Hi guys, welcome to the Ionic Compounds video. I am Ms. Eller and I will be walking you through page 3 and 4 in your blue notes packet. Before we begin, it's important to remember exactly what ionic compounds are made of. Ionic compounds are made of metals and nonmetals. You can find the metals on the left-hand side of the periodic table and the nonmetals on the right-hand side of the periodic table, separated by the zigzag line. In an ionic compound such as sodium chloride, NaCl, the metal sodium is listed first and the nonmetal chlorine is listed second. When writing formulas for ionic compounds, it's important to remember that ionic compounds are always written with the positive ion first, followed by the negative ion. Step 1 in determining the formula is to know the charge or the oxidation number of each ion. We know this from our periodic table. As a class, we have labeled all of our oxidation numbers on your yellow periodic table. We have previously skipped the center section known as transition metals. That is because transition metals have various charges and we were unable to predict their charge by the patterns that we could our other representative element groups. As we move through our notes, it tells us if you need a charge for a metal that's in our transition group, it will be given to you in the name of the compound by using a Roman numeral to indicate the charge. It tells you its charge in the name. So in our first example, actually example 1 and example 2 talk about copper. Copper is here in our center transition metal area group. In the example, copper 1 chloride, the Roman numeral of 1 tells you copper's charge is a +1. In our second example, the Roman numeral 2 tells you copper is a +2. In our example 3 and 4, we are discussing lead. Lead 2 chloride, the Roman numeral 2 tells you its charge is a +2. And lead 4 chloride, the Roman numeral 4 tells you lead's charge is a +4. If you are unfamiliar with Roman numerals, take a moment to write these numbers down into your notes packet. Writing formulas for ionic compounds, step 2 through 4. As I move through these steps, I'm going to be using the example of magnesium chloride. Step 2 tells us to write the positive ions formulas first and then write the negative ions formulas second. Step 3 says to write the charges above each ion. As I look at the periodic table, I find magnesium and it's in group 2, so it has a +2 charge. I find chlorine on the periodic table and it's in group 17 and it has a -1 charge. Now that I've completed step 3 and finding the charges above each ion, I can then move on to step 4. Step 4 is very important. It asks us to crisscross or drop and switch the ion charges to create a neutral compound. So what that's asking you to do is to look at the charge of magnesium and you are going to bring it down. You're going to crisscross it down to chlorine, subscript level. And then you're going to look at the charge of chlorine, it's -1, and you're going to bring that down to the subscript level for magnesium. Notice I did not bring down the plus or the minus, I only brought down my numbers. So my final formula is MgCl2. We do not write ones, our ones are understood, so they're left out of the formula. The last part of step 4 says if the two subscripts can be reduced, then do so. What this is asking you to do is find a common denominator. Our 1 and 2 are in the lowest terms, so they do not need to be reduced. We will see some examples where they are going to need to be reduced in future pages. Now we have several examples of writing ionic formulas. Please make sure to have out your periodic table so that you could follow along with the ionic charges for each group. The first example is barium iodide. It lists that barium is in group 2, so it has a +2 charge. Then it says that iodine is in group 17 and it has a -1 charge. When you crisscross those charges, the 2 comes down to the iodine, the 1 comes over to the barium. So your final formula is BaI2. Our next example is calcium oxide. Calcium is in group 2 and it has a +2 charge. Oxygen is in -2 because it's in group 16. So when we crisscross those charges, your 2 comes down to the oxygen, and then your second 2 comes over here to the calcium. So you're now left with Ca2O2, and this is our first example where our subscripts can be reduced. The common denominator allows you to reduce both by 2, which means your final answer is just Ca1O1, where we don't write our 1s. The next example is copper to chloride. Copper is a transition metal, and the Roman numeral tells us what copper's charge is. So copper is a +2. Chlorine is in group 17, and its charge is a -1. When we crisscross our charges, we have our 2 from our copper comes down to the chlorine, our 1 from our chlorine comes over to our copper. So our final answer is CuCl2. Sodium nitrate includes a polyatomic ion, and the polyatomic ions do not have to be memorized. They are found on the back of your periodic table in this location right here. You just have to know where to find them. So sodium nitrate, in the next example, the sodium is in group 1, so it receives a +1. Nitrate we find on our periodic table, and we find its formula to be NO3 and its charge to be a -1. When you crisscross those charges, the 1 comes on the outside of your NO3, and the 1 from the NO3 comes down to the sodium. Your final formula is NaNO3. If we had a subscript that was larger than 1, then we would need to use parentheses around our polyatomic ion, but because there is not a subscript larger than 1, then we can leave it off and it can be dropped. The next 4 examples I would like you to try on your own. Please pause the video and take a moment to work them out, and then when we come back, we'll discuss the answers. Your first example that you are supposed to do on your own is lead 4 sulfide. Your final answer for lead when you crisscross comes out to Pb2S4. But don't forget, when you have subscripts that can be reduced by the same number, the common denominator of 2, your final answer comes out to Pbs2. Magnesium sulfate includes a polyatomic ion. So when you look at your polyatomic ion chart, it tells you that SO4's charge is a -2, magnesium is a +2. When you crisscross those, you get Mg2SO42, but don't forget, they need to be reduced as well. They have a common denominator of 2 as well, so that your final answer is just MgSO4. Iron 3 fluoride. The Roman numeral tells you that iron's charge is a +3, so when you crisscross those, your final answer is FeF3. And then aluminum carbonate gives you a polyatomic ion, and this one is important because when you crisscross your aluminum's charge of 3 to the outside of your carbonate, you need to protect your polyatomic ion by using parentheses. Anytime that you have a greater than 1 on the outside of a polyatomic ion, then you're going to need to use parentheses. When naming ionic compounds, you simply name your 2 ions in the order listed. So the metal is listed first, and the metal's name is unchanged. In the example sodium chloride, NaCl, sodium's name is unchanged. In the example magnesium chloride, magnesium's name is unchanged. Naming ionic compounds, there's going to be some special cases with our transition metals in which we're going to have to work backwards from the formula to figure out what charge was being represented. In our first example, it talks about 2 different versions of copper, CuCl versus CuCl2. In CuCl, in this first example, we do not know copper's charge. Remember, copper is a transition metal, but we do know chlorine's charge. Chlorine's charge is a -1, it's in group 17. But as you work backwards and you realize that the 1 was brought down here, you ask yourself what was brought down from the copper in order to give you your final formula of CuCl. And the answer is 1. It must have been a 1 to work backwards. So your final name is copper 1 chloride. In our second example of CuCl2, the same thing happens again. You do not know copper's charge because it's a transition metal, but you do know chlorines. So chlorine is a -1, it's always a -1, and it was brought down here. But what was brought down from copper? Well, in the final formula, CuCl2, it must have been a 2 that was brought down. So its name is copper 2 chloride. You have to uncriss-cross those subscripts in order to get the charge. Now the following 2 examples can be very tricky. PbO is first. PbO, we do not know lead, but we do know oxygen. Oxygen's in group 16 and it's a -2. So as we work backwards, we know that the 2 came down here to lead, but we're asking ourselves what must have came here from the lead originally. Well, it ends up being Pb101, and right now we know that Pb has a subscript of a 2. So it must have been Pb2O2 that was reduced to give us PbO. So the answer was a charge of 2. Our second example of PbO2, we start again with only knowing that oxygen is a -2. But here's the difference on this one. Your -2 has a subscript of 2, which means this side of your formula has a -4 overall charge. The net charge of the entire compound is 0. So what that means is that this half of the compound must have been a +4. For the left-hand side must have been a +4 because the right-hand side is a -4, so the net charge is a 0. When you work backwards in that way, you can see that Pb2O4 was then reduced to Pb1O2. The second half of naming ionic compounds comes from your nonmetal. You start with your metal, your sodium, and you end with your nonmetal. You change the ending of your nonmetal to IDE. Instead of it saying sodium chlorine, it now says sodium chloride. In our second example, magnesium is our metal and it stays the same. The ending of our nonmetal is changed to IDE. So sodium chloride and magnesium chloride. Polyatomic ion names, when you're looking on the back of your yellow periodic table, are not going to be changed. They are going to stay the same. So in our example, sodium nitrate, the nitrate is exactly how it is on the back of our periodic table. The ending of our polyatomic ion names does not get changed to IDE, it just stays the same. As we begin our examples, it's important to realize that there are 3 different categories of ionic compounds. The first category is just regular ionic naming rules. These rules state that you name your metal first, and then you're going to name your nonmetal by changing the ending to IDE. Our first example is a regular ionic compound. First you list your metal, lithium, and then you list your nonmetal, chlorine, changing the ending to IDE, so your final name is lithium chloride. Our second naming rules include ionic compounds with transitions. The ionic compounds with transition naming rules include naming the transition metal, and then you are going to place a Roman numeral after the metal indicating the charge of the transition metal. And then third, you're going to name your nonmetal by changing the ending to IDE. Examples 2 and 3 both include transition metals. So following these rules, I'm going to name my metal first, my transition metal first. Sn is 10. And then as I work backwards, I know that my subscript of 2 is telling me what tin's charge is. So that's why I have a Roman numeral of 2 to tell my reader that we're using tin to fluoride. So fluorine's ending gets changed to IDE. On my second transition metal example, I work backwards and know that my subscript of 4 for my fluorine is going to tell me tin's charge, so I have tin for fluoride for my third example. Our third ionic compound group includes ionic compound naming with polyatomic ions. As you become more familiar with your polyatomic ions, you'll be able to recognize them more easily. But remember, you don't have to memorize them. They're on the back of your periodic table on the left-hand side in this section. So as I look at number 4, I notice NO3 is a polyatomic ion. So using my rules, the first thing I do is name my metal, sodium, and then I'm going to name my polyatomic ion NO3 nitrate. 5, 6, 7, and 8 also include polyatomic ions that I can recognize from the back of my periodic table. So number 5, I list my metal, zinc, and then I list my polyatomic ion, carbonate. Number 6 is special. Number 6 starts with the polyatomic ion, ammonium, NH4. The second half is your nonmetal, bromide. It's bromine, and the ending has been changed to IDE just as it did in your first section of your naming rules. Number 7 is silver phosphate, naming your metal and then naming your polyatomic ion. And number 8 includes a transition metal. This combines both the ionic naming rules of transition metals and the ionic naming rules of polyatomic ions. You have to work backwards in order to know which iron you used. What we know so far is that phosphate's charge is a -3, and we know that by looking on the back of our periodic table. So seeing our final formula as Fe1, PO41, we must know that Fe was also a +3. Iron 3 phosphate is our final name by putting our iron's charge in parentheses, the Roman numeral in parentheses after the metal. If you would like to take a moment to write down these 3 categories naming rules, please pause the video and do so. Now our video is complete and you may start to work on your practice packet pages 2 through 4. Be sure to ask your teacher for assistance if you have any questions completing this assignment.